Mathematics is built up logically, and a central concept within mathematics is a statement. And the statement can be true or false. Often you denote statements by capital letters, for example A, B, or X, Y. And examples of statements are, for example, it is raining. This is either true or false. Or B, the weather is cloudy. But those are not very mathematical statements, but still statements. A more mathematical statement is there are infinitely many prime numbers. And this is true, but that should be proven. Or a more succinct mathematical expression, for example, A less than B. And you can put quotation mark here just to see that what constitutes the proposition. Note that the truthness of the statement D, it depends on what A and B is. And of course, if it's not numbers, it's just meaningless. It's neither true or false. But if it's number, it could be true or false depending on what A and B is. The negation of a statement. So let's say you have a negation of a statement X, then you denote that by X bar. You can also denote it by this in front, but so there are different symbols, but we will stick to this. And this is the opposite of X, so it means not X. So that's the opposite of X. For example, if X is it's raining. And then of course X is it's not raining. If X is true, then the negation of that opposite is not true, it is false. And if X is false, then this is true. So one of them is true, while another is false. Note that, for example, that if we have a statement like the object is white, then the opposite of that is not the object is black. Maybe in language, but not in logic. So the object is not black does not mean that it is black. This means that it has a color other than white. So it could be pink or green or whatever, as long as it's not white. So the opposite of object is white is the object is not white, it has a color other than white. So you have to separate what you mean in language and what you mean in logic. And for example, we had a statement that A less than B. What's the opposite of that? The opposite of that is not A larger than B, but A larger than or equal to B. So that's the negation of that. You can combine statements. For example, if you have two statements A and B, you can combine them. For example, you can put this sign in between, and then that means A and B. And this statement is true if both A and B are true. So for example, if A is raining and B it's 1 plus 1 is 2, then if it is raining and 1 plus 1 is 2, then the whole thing is true. But if it's not raining and 1 plus 1 is 2, then this is false, but this is true, but then the whole thing is false. So both of them must be true for the whole thing to be true. Okay, so this symbol means and. Then you also have the symbol like this. And you can recognize these from Venn diagram in probability theory or set theory. So similarities. But here that means and this means or. So this means A or B. But then it's important to keep in mind that in logic, or means what we'd say in ordinary language as and or. So this A or B, that's true if at least one of these are true. So you have if this is true, or that is true, or if both are true, then the whole thing is true. The only time the whole thing is false is if both are false. So or is not excluding or, but it's and or meaning of or. Okay, so in logic that means at least one or and or. Okay, so for example, if you have 1 plus 1 is equal to 2, and 2 times 3 equal to 5, then this is true. This is of course false, but this is true. So the combined statement is true. Just one of them have to be true. And if we would have changed this to 6, then both of them are true, and then also the combination is true. Another way to combine statements is to put an arrow between them, or a special type of arrow. Arrow, I should say, not error. A, arrow, B. That means implies. A implies B. So that, for example, if we have it rains, then that implies that it's cloudy. So logically, this means if it's raining, then it must be cloudy, because it doesn't rain from a clear sky. But the opposite is not true. We cannot change the arrow here. It's cloudy does not imply that it rains. It can be cloudy but still not raining. So it rains implies it's cloudy, but it's cloudy does not imply it rains. So this means a logical implication. So it's not like a causal or something, it's a logical implication. Let's take another example. Let's say a squared is equal to 1. Then it logically follows that a is equal to 1 or a is equal to minus 1. So this implies this. But the opposite in this case also true. So we have implication also in the other direction. So in this case we do actually have implication from this to this. And if we have implication in both directions, we write it simply as a double pointing arrow. So this means that A implies B and also B implies A. This is called the equivalence. So when A is true, B is true, and when B is true, A is true. And if A is false, then B is also false, and vice versa. Note that if you have, for example, A, it rains, and B, it's cloudy, then we have that A implies B, but B does not imply A. But what is the case actually is that we have this. not B actually implies not A. And that's not just particular for these two examples. This always holds. So if A implies B, then the negation of B implies the negation of A. So for example, what does that mean in this case? So what is negation of A here? It rains. That it does not rain. And B is it's not cloudy. So this means here then, in this case, it's not cloudy. So if it's not cloudy, then it must follow that it does not rain. So you see that in this case, it's not cloudy logically implies that it does not rain. So we always have this A, if A implies B, then we also have that not B implies not A. But in general, we do not have that B implies A. We can't just turn the arrow around. Now we also have to change to negations then, because otherwise it's not true. So this is not always true. The importance of equivalence, that is A implies B and B implies A, the arrow in both directions. This we have already talked about, for example, when talking about solving equations. So if you press the I here up in the corner, you will get a link to where we solved equations. And we saw that equivalence was essential to solving equations. So that has to do with the two equations having the same solution. There we use the equivalence, there we use logic. So if you want to see the point of, or relevance of equivalence, go to that.